Okay, this video is going to detail some basics and some new vocabulary around the atom, but then it's also going to get into some properties of different atoms and being able to differentiate atoms of different elements based on some of those properties. So the first new vocab up, we've talked about just a little bit earlier this unit with a variable and an equation, but the first one is called nuclear charge. And so this seems pretty fancy, but all this means is the charge of the nucleus. And so if you remember, the things that are in the nucleus are protons and neutrons. Well, neutrons have no charge, so they don't contribute to the nuclear charge. The nuclear charge is simply the protons. Okay, and the variable that we use for this is Z. We saw that in a formula earlier this unit. So the nuclear charge, the big idea that you've got to get down about the atom is that the nucleus is sitting in the middle and has a positive charge. And then the electrons are all around it in different orbitals, different energy levels, the things that we've been working on locating them. But the nucleus is the thing trying to hold this all together. So if the nucleus weren't pulling all of those electrons in toward it, the electrons would fly off and just be whizzing all over the place. And when the electrons escape or move between atoms, that's what we do with chemistry, and we have reactions and different compounds forming. So the idea with this nucleus is the closer those electrons are to it, the more attracted they're going to be. The further they get away, the weaker and weaker that hold is. Okay, and then the other idea that we're going to get to is the more protons you have in here, okay, the stronger they're gonna hold their electrons. And so that's what we're going to kind of track through this whole video, is looking at how the number of protons and how far they are from those electrons affects different properties of the atom. So there are two other vocab terms that we're going to get to before we look at some pictures of some atoms. So first up is something called shielding. So if you think about what you know as a shield always gets between you and something else. So a shield literally gets in between. And so there's the definition for electron shielding is that one electron repulses another and it reduces the attraction of the nuclear charge. So the idea is that the nucleus sitting in the middle is pulling in on electrons. So it's trying to drag in the electrons. But if you get another electron in the way, let's say an electron right here sitting in between them, that electron is repulsive to that other electron out there. So it actually pushes out while the nucleus is trying to pull in. Okay, and so you have a little bit of a battle there, but a shield is that electron that gets in between. So I'm going to have a different picture of that drawn for you, so you can count those up a little bit better. But that's all that a shield is it literally has to get in between. So the other vocab word here is something called the effective nuclear charge. So it's a little bit of a modification on the nuclear charge that we just went over. But we use the Z for nuclear charge, and then we put a little subscript EFF for effective. So it's the effective nuclear charge. But this is the nuclear charge that the electron, whatever electron we're looking at, that it actually experiences. We're going to learn a little math equation, but all the ZF is the Z, the number of protons, and you subtract out the shielding. Okay, so it's just the nuclear charge, but reduced by any shielding. That's all that is. So we're going to look at several elements on the periodic table and see if we can identify some different things about them. So we're going to start in period 2 on the periodic table, and we're going to look at 4 different elements here, and then we're going to look at some other elements in group 1. So up at the top, I have a little formula for ZF. So what we're going to do with several of these is we're going to come back to these pictures throughout today, but we're going to calculate some ZFs, we're going to look at their electron configurations, and we're going to then see what these ZFs, the electron configurations, do to the properties of the atoms themselves. So if you look at lithium on the periodic table, lithium has 3 protons. So its 3 protons are going to be located in the nucleus, right in the middle. Okay, but we have learned now that the electrons, we also have 3 electrons, but those aren't located in the middle, and we've spent time with electron configurations. So we have 1s2, 2s1. That's where lithium's 3 electrons are. So this drawing right here is a bad drawing of what we are now using as the atom with the electron cloud, but that gets really complicated to draw with all the different shapes, so I'm going to simplify it down and just show the energy levels as these little rings. So this first ring right here is going to be energy level number 1, and then the second ring is going to be energy level number 2. And all we're going to do is place some electrons in there. Okay, so if we look, our electron configuration says there are 2 electrons in energy level number 1. We're not going to worry about the shapes right now. So we're just going to put 2 electrons in there. And then there's 1 electron in energy level number 2. Okay, so if I went through these different variables up here, Z is the nuclear charge, so it is just 3. It's a positive 3. Okay, what you next have to identify is what the shielding is. And so it depends on which electron you're looking at. So if you were asking about that electron right there, there is no shield between it and the nucleus. There's nothing else in between it and those 3 positives. So it would be no shield. When we generally talk about shielding, when we start talking about atomic properties as a whole, we usually look at the valence electrons, which if you remember from last week is the outer electron. And so this right here out in energy level number 2 would be one of our valence electrons. So we're going to look at that. And so then what we ask ourselves is, how many electrons are physically between that electron on the valence and the nucleus? So that pull right there, that nucleus is trying to drag that electron toward it, how many electrons are in between that? So all you do with shielding is it's the inner layers. How many electrons are sitting on the inner layers? And so you think about this, we do this all the time. If we go outside and it's chilly outside, well, what is there to shield us from that cold? What is there to shield our bodies? Well, it's any layers of clothing that are between our physical body and the elements themselves, the outdoor, the air. And so every layer of clothing we'd have on would count as a shield. And so for this particular element right now, the shielding is a 2, because there are 2 electrons that are sitting in between that nucleus and that electron on the outside. So when we look at the ZF for this electron, what we're talking about is what charge does it actually feel from the nucleus. So these inner electrons right here that are really close to that 3+, they feel the force or the strength of all 3 of those electrons. But when we look at the outer electron, it's not going to feel as strong of a force of attraction from that nucleus, not only because it's farther away, but also because those electrons in between it and the nucleus are helping to push it away. They are repulsing. Okay, so when we calculate ZF, we take the protons and we subtract the shield. And so we just get a positive 1. So we say this electron only feels the force of 1 positive. Okay, so then we're going to move over to beryllium and do the same exact thing. So beryllium, we look it up and it has 4 protons, and then it has 4 electrons, but we're going to look at where its electrons are located, because all 4 of the protons sit right in that middle. And so the 4 electrons are in 1s2, 2s2. So when we go through our list of variables, our Z is 4. That's our nuclear charge. That's what's sitting in the middle. But then we have to identify the shielding. Okay? And so we have to draw those electrons in where they would be located. So I'm going to do 2 electrons in energy level number 1, and then 2 electrons in energy level number 2. Okay? And remember, where I'm placing these is not really where they're at. They're in a region in space in an orbital that's a shape. Okay, so it's not like it's on the left or the right, it's in some region. Okay, so when we ask about shielding, again, we're talking about one particular electron. So for an example, if I looked at this inner electron, there would be no shield between that and the nucleus. We're all looking at anything that gets in between the electron that we're looking at and the middle. Okay, but if I look at this electron, one of the valence, and I could pick either one, okay, it doesn't matter. If I look at the valence electron and I ask myself how many electrons are between that and the nucleus, I have to look at the inner layers again. Okay, and so even though I drew one on the left and one on the right, it's not like that. They're in an area around there. They are both in between. They're an inner layer. So that shielding is again 2. So we don't count this guy out here because he's not in between the nucleus and that outer electron. It's at the same distance away. So when we go calculate ZF for this electron on the outside, we take our 4 and we subtract our 2 and we get a positive 2. So we're saying that electron on the outside feels the force of 2 protons. Okay, it's essentially that nucleus has been weakened a little bit because of that shield. Okay, and then when we look at boron, one more to the right, we'll come back to fluorine in a little bit. Okay, boron has 5 protons. And so those 5 protons are going to be located in the nucleus, right in the middle. Okay, and then we've got 5 electrons, but they have their own location. So we have 1s2, 2s2, 2p1. Okay, so I'm going to go place those, and 2 of them are going to sit in energy level number 1. And even though they're in different shapes, which I'm not drawing here, there are 3 total electrons in energy level number 2. Okay, so if you go and answer these 3 variables again, our Z, our positive charge of our nucleus, is a 5. And then our shield, okay, and again, pick your electron, but I'm going to pick one of these valence. Okay, our shield, so anything between that and the nucleus, so they're just the inner layers, okay, is once again 2. So our ZF for this electron right here is 5 minus 2, which is a 3. Okay, so a positive 3, I guess. And so one thing that I do want you to note, okay, as you're looking at these, you're going, well, why is my shielding the same every time? If you go look at these 3 elements on the periodic table, you will find that they're all located in energy level number 2. That's where their valence is. Okay, we have lithium, beryllium, and boron. So they all have 2 energy levels. So that means all of them only have 1 layer in between the nucleus and their outside. So their shield was the same every time. What's changing is their number of protons in that middle, and it's affecting that effective nuclear charge. Okay, so then if we move along to sodium, okay, so sodium now, I've drawn where these are in relation to each other on the periodic table. That's why we're going down now. So sodium has 11 protons. It also has 11 electrons, but those electrons are in different locations. So we have 1s2, 2s2, 2p6, 3s1. So if we go draw those in there, okay, we've got our 11 pluses sitting in the middle, the very middle, that's our nucleus. And then we've got 3 energy levels now. So that's why I have these 3 rings drawn. So we've got 1, 2, and 3. So we're going to put 2 electrons in the first energy level. And then the second energy level, in different shapes, we have a total of 8. 3, 4, 5, 6, 7, 8. And then in energy level number 3, we've just got 1 electron. So if I was asked for Z, I would give 11 positive. It's 11 protons in that middle. Okay, and then on the shielding, okay, so I want to go through a couple things for this. So if I had asked you, what is the shield for the electron I just highlighted? It would be 0 shield. There is nothing between that and the nucleus. If I asked about what is the shield for the electron I highlighted again, in that second energy level, the shield would be 2 this time, because the only electrons between it and the nucleus are those 2 that are sitting in energy level number 1. Okay, but again, most of the time when we talk about shields, we are looking at the outermost electron in the valence. So if I ask you about the shielding for that electron out there, you have to account for all of the layers that are in between that electron and the nucleus. So both of those energy levels that I just highlighted and all of those electrons will count as shielding electrons. So if you add those all up, you have 2 from the first level and 8 from the second. That gives us 10 for the shield. So when we look at the effective nuclear charge for that electron, we would get 11 minus 10, which is 1. A positive 1. Okay? If, just to show you the difference, if I looked at the electron I just circled in pink and calculated ZF for this one, I still have those 11 protons, but for that electron that I circled in pink, only has a shield of 2. So it would feel 9 protons because there's less of a shield and it is closer to that nucleus. So it would feel more. So the ZF is definitely dependent on which electron you are. Okay, what you feel from the nucleus. Okay, it's the same thing that happens in class. The students that sit in the front row feel a much bigger obligation to be paying attention most of the time. because they're closer and there's nobody protecting them, shielding them from me. They're less likely to be on their phones, maybe, depends on the person and who's talking, but they're less likely to do that versus the student that sits in the very back, four rows away from me, feels less of a force coming from me. Okay, so then we're going to do one more of these before talking about some trends. So we're looking at potassium next. So potassium has 19 protons, so all 19 of those guys located in the nucleus, and then its 19 electrons are in 4 different energy levels. We get 1s2, 2s2, 2p6, 3s2, 3p6, and finally 4s1. Okay, so if we look and put these on the drawing, we put 2 of them in energy level number 1, and then we have 8 in energy level number 2. Okay, and then we have another 8 in energy level number 3. And then we finally have 1 in energy level number 4. So if I give you the Z, or ask for the Z, it would be 19. If I just ask for the nuclear charge, that's what it is, 19. Okay, and then we're going to talk about several shields again because I want you clear on this, that the shielding is definitely dependent on what electron we're looking at. So if I ask electron I circled in purple, the shield right there is 0. There's nothing between that and the nucleus. Okay, if I ask this electron that I circled in purple, the shield would be 2, because those 2 electrons that I just highlighted are between it and the nucleus. Okay, if I ask this next electron that I circled, the shield you would have to account for both of these first layers, and the shield for that guy would be 10, because you have 2 from the first level and 8 from the second. If I ask finally for 1 out here, you have to account for this third energy level also as shielding. Okay, so if I do that and ask about the shield for that electron, what I would do is I'd have 2 and 8, which makes 10, and another 8, which makes 18. So then if I find the ZF for that electron, I would have 19 minus 18, which is a positive 1. Okay, so that's a detailed explanation of how to calculate those all, shielding and ZFs and all that kind of stuff. Those are responsible for all of the little trends and properties that we're going to talk about. So one thing I do want you to notice on the ZFs, because I arranged these how they are on the periodic table. Okay, so I want you to look at the shielding and the ZFs for all of these, and then look at what happens on how they're related on the periodic table. So we already talked about the first 3. As you go across the periodic table, lithium, beryllium, boron, the shielding is staying constant. But what's changing is the number of protons, which makes the ZF increase. So that electron that's sitting on the outside is going to feel more from the nucleus as we go across that periodic table. If you look at the lithium, sodium, potassium situation and find them on the periodic table, they're arranged in the same family. Okay, and when we talked about at the beginning of the year, families have similar properties. They start behaving very similarly. And so this is why it has to do with their electrons. And so if you look at all these, as you go down the periodic table, lithium, sodium, potassium, their shielding is vastly different. And why their shielding is vastly different, we went from 2 to 10 to 18, is that you get more energy levels as you go down the periodic table. So there's more and more inner layers because your outer layer is always one bigger. So that shielding is going up. So if you look at what's happening, though, to the ZF, it's exactly the same every time. That family all feels 1 for their valence electron. And this whole family tends to lose 1 electron when they interact with other atoms. Okay? So that's what shielding and nuclear and effective nuclear charge are. But we're going to talk about how it's related to some other properties. Okay, so what we're going to do is we're going to discuss a couple periodic trends, and we're going to try to do 2 today, and then we'll spend time in another day doing the other big one that you need to know. Periodic trends are things that we notice happen as we go through each period, or as we look different periods in the same family, and we see the same things happening over and over and over. these, though I need to impress upon you, these are observations that we have noticed. Where they are on the periodic table is not why these happen. What we're going to talk about is all of their electrons and where they're located and how they behave is why we put them where they are on the periodic table. So if I were to arrange you in a line, all the students in class, from the shortest student to the tallest student, and I arranged you all like that, and then I ask, well, why is this kid taller than this kid? It's not because they sit to the right of them or whatever. It's not because I arrange them that way for why they're taller. That's a whole different situation that has to do with their genetics and maybe their environment and all kinds of other things, but it has nothing to do with how I arrange them. So all of these trends that we learn, we built the periodic table around them. The periodic table does not force them to be this way. So you will never be, if they ask you to explain why this one is bigger than this one or smaller than this one, it's never because it's to the right or to the left. We arrange them because we notice that, okay, to help us out and simplify it. But why it is like that has to do with its protons and its electrons, and that's what we're going to look at. And so what the dominating factors in each of these is the effective nuclear charge, what the electrons feel from that nucleus, and then how many darn energy levels the atom has, because those definitely affect some things. Okay, so I did want to do a quick reminder. If you guys remember Coulomb's law, Coulomb's law talked about how charges were attracted or repelled by each other. And so what we're looking at here, Coulombic attraction, we're going to try to see if what's going to attract other things. We have to have opposites attract. So our positives and our negatives, our protons and electrons, are going to attract each other. Electrons and other electrons will repel each other. But the idea in Coulomb's law is the bigger the charges are, the more pluses and more minuses you have, the bigger that attraction is going to be. And then also the distance matters. How close they are also affects how strong that is. So I'm sure you've done this with magnets. If you've got them on the attractive direction, the closer they get, the stronger and stronger that force becomes. When you get them far enough away from each other, you don't even feel any attraction anymore. There's no pull together. So if I asked you to rank these charges in order of decreasing attraction, decreasing, so that means high attraction to low attraction. Okay, first of all, we want to look at which ones are actually attracted to each other. And so if you look at A, B, and C, those are all opposite charges. So those are all going to be attracted to each other. D are opposite charges. So D should have the lowest attraction because it actually is a repulsion. Okay, so then if you had to rank the others, okay, the two things that are going to matter are the charges and then the distance between them. So the closer they are, the stronger that attraction is going to be. So if you look at B, those are pretty close to each other, versus C, those are farther away from each other, but they're the same charges. So B is going to have a higher attraction than C. And so then the last thing to do is to rank A. So we have to figure out how A relates. And if you look at A versus C, those are roughly the same distance apart from each other. However, C has bigger charges. Bigger charges are going to lead to a bigger attraction. So C is going to be higher than A. So the order that they would go from high to low would be B, C, A, D. All right, so the first part that we're going to look at is atomic radius. Okay, so atomic radius is simply the radius of the atom. So I'm going to go back to those drawings. So radius, you've learned in hopefully math class, is the distance between the middle of a circle to the very outside. So that's why we've been focusing on the valence, is the outside defines on how big this thing is. So atomic radius, simply from the middle, so from the protons to the outside. So the easy one for you guys to note is if I look at lithium, sodium, and potassium. Okay, if I had to draw the distance between the middle and the outside and compare them to each other, you should see that the atomic radius, that distance, is getting bigger. Okay, so down the periodic table, okay, that's how these guys are related to each other, but down the periodic table, atomic radius increases. Okay, and the reason why, okay, is because you have more shielding, or you can just say there's more energy levels. Okay, as you go down, it's going to get bigger and bigger and bigger because you have more energy levels. Okay, because we're going to start ranking elements against each other and see if you can predict who's bigger and who's smaller. And the periodic table is arranged beautifully for you to be able to predict, but it is not the reason. The reason has to do with how many energy levels here. So the harder one to do is what happens to the atomic radius as we go across the periodic table. So if you look at the 3 elements that we've drawn in, they all look about the same size because they all have 2 energy levels. But there is going to be a difference in the size, and I was not able to draw the minute differences in their size with the little circles I was using. So this one, you're just going to have to understand this one. It's not as easy to see visually. So if you look, and they all have 2 energy levels. What we're looking at is how far that second energy level, which is the outer one, can get from that nucleus. That nucleus is trying to drag that back in, that valence shell back in. Okay, so the nucleus is pulling that valence shell in toward it. And so the question is, or the idea is, the smallest atom, the one that ends up being the smallest size, will have that has the smallest radius, will be the one where the nucleus pulls that second level in the tightest. And so the thing pulling those electrons in is the nucleus, which is the protons. So if you look at the difference in the protons, okay, lithium only has 3 protons that are dragging that second energy level in. Beryllium has 4 protons that are dragging that second energy level in, and boron has 5. And so what happens to the atomic radius as you go across the periodic table is it decreases. And why is because you have the same number of energy levels. Okay, that is key. But the protons increase as you go across. And some people will just say, for energy levels and protons, we'll simplify this down to ZF increases. Okay, and that's what's happening if you look at our ZFs. That was going up because the protons kept going up every time, but the energy level, which is responsible for our shielding, kept staying the same. So that's what the ZF is. And that's really hard to get in your head, that the bigger the protons are, the smaller the atom is. But you got to remember, the protons are the things sucking everything in toward it. So they're pulling them all in toward them, which makes the atom smaller. Okay? So what the periodic table helps us do is, if you know these general trends, you can try to predict whether an atom is bigger or smaller than another atom based on its position. Its position is not Y, but we use that to kind of cheat and go, it's over there, so it must be bigger than this. Because we already know, we arranged like that based on its energy levels. Okay, so we're going to try to practice a couple of those. Okay, this is a little picture of roughly what the periodic table, looks like graphically, with all the little atoms written as circles. And as you can see, as you go down the periodic table, you get bigger and bigger and bigger because there are more and more energy levels. And as you go across the periodic table, the atoms get smaller and smaller and smaller because they have the same number of energy levels as they go across, but more and more and more protons, which are sucking in the electrons. Okay, so we're going to try to rank them. Okay, using the periodic table. Okay, this one asks us to rank them in order of decreasing atomic radius. So the first thing when you do this is to make sure you understand what that means. So decreasing means we're going to go big to small. That's the order that we want to rank them in. Okay, so we're going to find these 3 atoms in each set and see if we can rank them. So we got calcium, magnesium, and strontium. So calcium, magnesium, and strontium are right here on the periodic table. So if you had to figure out which one is the biggest, the idea of how they're arranged is, as you're looking up and down on the periodic table, okay, we're looking at energy levels. So energy levels get bigger as you go down the periodic table. All right, so out of these, magnesium only has 3 energy levels, calcium has 4, strontium has 5. So strontium is going to be our biggest, then calcium, then magnesium. Okay. All right, so then the next one up, next set is potassium, gallium, and calcium. So we have potassium and calcium here, and then gallium over here. So what you need to note on this is that since they're all in the same period on the periodic table, what that indicates is they all have the same energy level. They all have 4 valence levels. Okay, even though this one is in 4p and these guys are in 4s, there's still 4 levels. Okay, and so what our general trend is since they have the same energy level, but the more and more protons as they go across, the atomic radius decreases because the protons, additional protons, drag it in tighter and tighter. So this is the weird thing for students, but the biggest of these atoms is potassium because it has the least amount of pluses that are dragging in those 4 energy levels. Okay, then calcium, and then finally gallium. So gallium has 11 more protons than calcium, or than potassium, sorry, that are pulling in those 4 levels, and that's why it ends up being tinier. Okay, so the trends are super nice so that you don't have to go through that whole discussion each time to see if you can predict. So in general though, I'm going to do the rest of them. But if atomic radius decreases as you go across and increases as you go down, then francium should be the biggest and helium should be the smallest. Okay, that's just generic. All right, so then next 3, we've got bromine, rubidium, and krypton. So rubidium, bromine, and krypton. So these guys are a combination of the 2 that we've been doing. They have different energy levels. One of them has a different energy level than the other 2, and then 2 of them have the same energy level. So the most important one of those qualities that relates to atomic radius is the energy levels. Energy levels are much more important than the protons. The more energy levels you have, the bigger you're going to be. So if you look, rubidium has 5 levels and bromine and krypton only have 4. So rubidium is going to be the biggest atom out of those. It just has more energy levels. So then if we're comparing 4 levels to 4 levels like we are with krypton and bromine, then we look at the protons. And so we have to ask ourselves, who has more protons? Krypton has 36, bromine has 35. So krypton's 36 are going to drag its 4 levels in tighter. So krypton's actually going to be the smallest, and bromine is in the middle. All right, so next set, strontium, calcium, and rubidium. Okay, so we've got this little block right here. So first up, you got to look at energy levels. So we do have some differing energy levels here. So the two that are in energy level number 5 are going to be the biggest, which means calcium is going to be the smallest. I know that. Okay, but then out of rubidium and strontium, we want to know who is smaller out of those. And so if they're in the same energy level, then we're comparing protons. So strontium has 38 protons and rubidium only has 37. So strontium is going to pull its electrons in tighter. So strontium is going to be a little smaller than rubidium. Okay, then we've got selenium, bromine, and chlorine. Okay, it's the same situation with different energy levels. So I see that chlorine only has 3 energy levels. It's going to be the smallest. Okay, and then out of selenium and bromine, bromine has more protons in that same energy level. So bromine is going to be a little smaller than selenium. Okay, and then last set, we've got iodine, xenon, and barium. So barium, iodine, and xenon. So again, we have differing energy levels. Barium has more energy levels than the other 2. So barium's going to be the biggest. And then out of iodine and xenon, xenon has more protons, so xenon's going to be the smallest, and iodine's going to be in the middle here. So one thing, this is how you need to process and the thoughts. When you're ranking them, if you notice though, if I were going from big to small, I was generally going in that direction the entire time. Okay, up and to the right goes big to small. Okay, but the idea is energy levels and protons. That's what we need to look at. So then we've stayed away from a section on the periodic table. The D group, the transition elements here, we got to talk about what happens to their sizes. So they're a little bit strange. Okay, so I'm going to draw some atoms again. So if we go find the first two elements that are sitting in the transition block, scandium has 21 protons, and its electrons are 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. And then titanium has 22 protons, and its electrons are 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So when I go put these protons and electrons in their location, so we got the nucleus. Okay, we got 2 in energy level number 1, then we've got 8. And then in energy level number 3, when we first start, we go 1, 2, 3, 4, 5, 6, 7, 8. Then we go on and put 2 electrons in energy level 4. But then we come back and put another one in level 3. So for titanium, do the same thing. Okay, we originally put 8 in energy level number 3. Okay, and then we go put 2 in energy level number 4. And then we go back and put 2 more in energy level number 3. So if we calculate the ZF, remember that when we look at the atomic radius, what we're looking at is the distance from the nucleus to this outermost electron. Okay, we want to look at that difference. And so the Z for scandium is 21. The Z for titanium is 22. And then when we look at the shield, okay, if we're looking at the outer electrons, we got to count everything in between. So energy levels 1, 2, and 3. So if you go through and count those, I believe you have 19. We had 2 and 8 is 10, and then we had another 8, 18, 19. Okay, and if you do the same thing over for titanium, our shield for this outermost electron, we'd add up all of the inner energy levels. Okay, and we should get our shield is 20. So then when we look at the ZF for that outer electron, for that guy, we get 21 minus 19, which is a positive 2. When we do the same thing for the outer electron in titanium, we get 22 minus 20, which is a positive 2. So if you look at these two elements and you were trying to figure out which one's bigger or smaller, they both have 4 energy levels, so they look pretty much the same. Their shields are slightly different, but so are their protons. And so we have not had one where their protons differed and their shield differed, but the transitional elements are weird because as you add protons as you're going across, you also add electrons into the shield because those guys get added to the inner layers. So because shielding is going up at the same time as protons, you're left with the same effective nuclear charge. And so what happens with transition elements is their radii are about constant as you go across. They don't change much as you go across. Now when you go down the periodic table, they definitely change just like the other ones because they get more and more energy levels. But as you go across, they're fairly constant. Okay, so just to, I mean, it's not perfect, but just to show you the little graph. Okay, there are some weird anomalies, but in general, you'll see as you go across a periodic table from lithium to fluorine, that atomic radius was decreasing. From sodium to chlorine, atomic radius is decreasing. But when we hit the transition elements in the middle, there's this weird kind of flattening out that happens. Okay, and so the reason why is that the shielding is going up, and so is the proton, so the ZF stays about the same. And the energy levels also stay the same, so you end up with the same. So then we're not going to do any examples on that. The last thing is about ions. What happens to an atom's size when you start messing with its electrons? So you remember back in the fall, we talked about anions and cations. Anions are the negatives and cations are the positives. So how anions get formed is they gain electrons, and cations get formed by losing electrons. So if you had to just take a stab at it, if you gain electrons, and electrons are the things sitting out in the rings, if you had to take a stab at what happens to the size, if you're gaining things on the outside, you're generally going to become bigger. Cations are losing electrons which are sitting on the outside, and they become smaller. Okay? And that's generally what happens. But you have to be a little careful on how you explain and what happens, because when you start changing all the electrons, things get really weird, and you have to look for exceptions. Okay? So in general, I'm going to show you this in drawing the pictures, but in general, this is what happens to the size. So let's say we had lithium and sodium and potassium, which I drew on the other diagram. If you lose an electron from lithium, okay, going back to this drawing. Okay, so if you look at this picture for lithium right now with its 3 protons and 3 electrons, when it loses an electron and becomes a positive 1 charge, the electron that it loses, it's going to be from its valence. So this electron that's sitting out here is going to disappear. Well, if there are no electrons in energy level number 2, energy level number 2 really doesn't even exist for that atom. And if you had to describe what happens to the size, that size just got a lot smaller. The same thing happens to sodium. Sodium tends to become a positive 1. It tends to lose this electron on the outside, which also loses that energy level. So that ion has become a lot smaller than it was originally. And then again with the potassium. Okay, so usually that's fairly easy to understand because you're losing an entire energy level. The harder part is what happens when it doesn't lose an entire energy level if it becomes a negative ion. So if we go study fluorine for just a second, okay, and we look at its protons and its electrons, so it's got 9 protons and 9 electrons, and they're in 1s2, 2s2, 2p5. So we put our 9 protons in the middle, in the nucleus, and then we've got 2 electrons in energy level number 1, and then we've got 7 in energy level number 2. Okay, and remember, holding that second energy level is those protons. They are dragging those electrons in, dragging them all toward them. Okay, so right now there are 9 protons holding 9 electrons total, and they're dragging in that second energy level. So what happens with fluorine is fluorine most often becomes the ion F-1, okay, which means it gains an electron. So it has space to put 1 more electron in this 2p, and it fills up that energy level. Well, when it gains that electron, it doesn't look like it changed size much. Okay, it's in that same energy level, but now those same 9 protons have to hold an extra electron on them. So if you imagine if you were, I don't know, you were a dog walker, and you had 6 leashes, and you were trying to hold all of them, and you had a certain amount of strength, and you were able to hold them at a certain length from you, as strong as you were and as strong as they were trying to get away, and someone handed you a 7th leash, and you were still the same person trying to hold them on, you're probably not going to have as good a grip on those dogs as you did before, because now there's an extra one pulling away. And so what happens when you become negative, when an atom becomes negative, is that those same protons have a little harder time holding on to those electrons, because now there are more electrons, and the atom gets a smidge bigger. Okay, this second energy level, I don't think I can do it, but gets a little bit bigger. Not a whole lot, but it gets a little bit bigger. Okay, so in general, the negative ions become bigger and the positive ions become smaller. Okay, so this is F, showing what happens to F as it gains electron, become F negative, Cl to Cl negative, and Br to Br negative. Okay, the trends up and down the periodic table still follow. When you change energy levels, those are still bigger as you have more energy levels. Okay, so we're going to see if we can arrange these. All right, so if you were asked to rank these ions in order of decreasing size, it's the same thing we just did. So that is big to small. However, the periodic table is not as useful this time because when you start giving it pluses and minuses, you've messed with the electrons. You've made them look different. So you have to account for what they look like now. So the things that always matter is energy levels and protons. So no matter how I change it, you can look at energy levels and protons. So I'm going to try to keep track of those for each one of these energy levels and protons. Okay, so for calcium originally had its electrons in 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. When it becomes Ca2+, it means you've lost 2 electrons. The electrons that are going to get lost always come from the outermost level. The outermost level. So the outermost level here is 4, so they're always going to come from level 4 here for calcium. So what's going to happen now is calcium, it still has the 20 protons, but for its energy levels now, it only has 3. So then we're going to move along to looking at strontium. Okay, so strontium, see if we can do this a little bit quicker. Strontium right now normally has 5 energy levels. It ends in 5s2. But when it becomes Sr2+, it loses that outer electron shell, and now it only has 4 levels. It lost its 5th level. It still has 38 protons. And then magnesium normally has 3 energy levels, and its outer electrons are 3s2. When it becomes Mg2+, it loses those 2, and it only has 2 energy levels now. It still has its 12 protons. So when you rank ions in order, you pay attention to energy levels and protons the same as before. It's just the periodic table doesn't help you as much with this in its natural organization because we started messing with things. So you look at what you've got. If the energy levels are different, you do not care about protons. Energy levels dictate everything. So since the energy levels are different here, we don't have to care at all about those protons. We're just going to go in order from big to small. So the biggest has the most energy levels. Okay, and the smallest is going to have the least energy levels. Those are fairly easy when it's the energy levels that are different. The harder part comes with when the energy levels are the same, and then you have to deal with protons. Okay, but if you understood the ranking before, this is going to follow the same thing. So first up, we've got K plus on letter B. K plus. So K, normally potassium, normally ends in 4s1. Normally has 4 energy levels. But if we lose an electron, as that positive means, we go back to having 3 energy levels. Still has its 19 protons. Sulfur is over on the right side, right here. Normally ends in 3s2, 3p4. But if we give it a -2, it means we've given it 2 more electrons. We can fit both of those electrons in the 3p and fill it all up. But that means it still has 3 energy levels. Okay? And it's 16 protons. And then Cl negative, Cl right here, normally ends in 3s2, 3p5. If we make it Cl negative, it means we've given it 1 more electron, and so we can fit that and make it 3p6. We can fill that up in the 3rd energy level, but we still have 3 energy levels. And chlorine has 17 protons. So the protons never, ever, ever change. That's nuclear chemistry, and we don't do that. Only the electrons are going to change, which can change the energy levels. So now if you're looking at this data and saying, okay, which of these is the biggest and which of these is the smallest, you got to get it straight in your head. These are the energy levels, so the total number of rings, and they all have 3. So that means we have to go to the protons, and you got to get straight in your head that the protons are pulling it in tighter. So the most protons that you have are going to end up at being the smallest atom because they pull in all of their electrons tight. So potassium has the most protons. It's going to be the smallest atom. Sulfur, sorry, I should have written it as potassium. Sulfur has the least amount of protons. It's going to end up being the biggest. It's harder to hold on to all those electrons with only 16 protons. And then chlorine sitting in the middle. Okay, so I don't know if you noticed this when we did this, but all of these guys, K when it lost 1, sulfur when it gained 2, or chlorine when it gained 1, all ended up having 18 electrons. The word for that was isoelectronic, when they had the same electrons. And they are all isoelectronic with argon. So they all have that full 3 energy levels, but their protons are different. Okay, and that's what you really have to gear up for. So we're going to go to letter D, and then E, and then back to C. C is a little strange. So if you look at D, we got Cl negative, Br negative, and F negative. So there's fluorine, chlorine, and bromine. When F becomes F negative, it gains one more proton, or electron, sorry, never change the proton, and it has 9 protons, but now it has 10 electrons. Well, 10 electrons is isoelectronic with neon, but that still has 2 energy levels. Okay, when you look at chlorine, chlorine has 17 protons. When it becomes Cl negative, it gains 1 electron, so it looks like argon. It's isoelectronic to argon, but it still has 3 energy levels. Didn't change any energy levels. Okay, and then the last one, bromine, okay, has 35 protons. When it becomes Br negative, it becomes isoelectronic with krypton, but that's still 4 energy levels. So if you had to figure out who's biggest of these guys, it doesn't matter what their protons are because their energy levels are different. So 4 energy levels is going to be bigger than 3, which is bigger than 2. So the biggest is going to be Br negative, and then Cl negative, and then the smallest is going to be F negative. Okay, so then E, which is a little more difficult, has Na plus, Mg2 plus, and F negative. Okay, so we already have F negative written out here, that F negative has 9 protons and 2 energy levels. Okay, but if we look at Na plus, so Na normally has 11 protons, and it normally has 3 energy levels, but when we make it 11 plus, we've taken away an electron, so we make it have 10 electrons. Well, that makes it isoelectronic to neon. Neon only has 2 energy levels. Okay, and then Mg2 plus, right here, Mg normally has 12 protons, and it should have 12 electrons, but if we've removed 2, so we made it Mg2 plus, it is also isoelectronic with neon, which means it has 2 energy levels. So all 3 of these elements, Na plus, Mg2 plus, and F negative, are all isoelectronic to neon, which just means they have the same electrons as neon, which means they have the same energy levels. So the difference then must be the protons. And so remember, protons are dragging things in. So the biggest atoms are going to have the least ability to pull things in. So F negative is going to be the biggest because it only has 9 pluses that are trying to hold on to 10 electrons. Okay, then sodium, Na plus, because it has 11 trying to pull on those 10. And then the smallest is going to be Mg2 plus, because it has 12 that are trying to hold 10. Okay? And then the last one that we'll do is a little bit of a weird situation. Okay, we've got Au plus and Au3 plus. Okay, so for Au, normally has 79 protons and 79 electrons. Okay. When you make it Au plus, you still have 79 protons, but now you have 78 electrons. We never ever change the protons. Okay, and then when you make it Au3 plus, what you've done, you still have 79 protons, but now you've lost 3 total electrons, which means you're down to 76 electrons. So this one's a little strange because we're comparing the same element to each other. These guys have the same exact protons, and the only way 2 elements can have the same proton is if they're the same elements. So then the question is, out of these 2 guys with the same protons, we got to figure out which one of these guys is going to be bigger. So these electrons are on the outside, and remember, okay, they have the same amount of protons. One of them is dragging in 76 electrons, and one of them is dragging in 78. The more electrons those same amount of protons have to drag in, the bigger that atom's going to be. So the biggest one here is going to be Au plus, and then the smallest is Au3 plus. That battle right there with only 76 electrons to its 79 protons, that protons win a little bit better on that and drag them in tighter. Okay, so that's it on the sizes of things. We'll learn 2 more trends the next class.